Hello, Professor Kung. My name is Ethan Graham, and I'm going to be showing my fluid and thermal systems project with you. So what I did for my project is I did Boyle's Law, which, as I'm sure you know, basically states that an ideal gas at a given pressure is inversely proportional to its volume at a constant temperature. So for this experiment, I've been using the TQ-TD1000 Boyle's Law apparatus. When I was over in Cyprus, they had one of these in the classroom that I was working in, so luckily I was able to use this. So it's comprised of a couple of parts. We have our two cylinders, one being the reservoir cylinder and the other the test cylinder. Next to the test cylinder, we have our height measurement tool that we're going to use to determine the volume as we increase the liquid levels in the test cylinder. We also have our pressure and vacuum tubes, and this pump right here is how I was able to increase the pressure during my experiment. And lastly, we have our pressure dial, which tells us the pressure that is being put into the reservoir cylinder, as well as our temperature measurement tool. So this was able to let me know if I was keeping the experiment at a constant temperature the entire time. So my hypothesis for this experiment was that knowing what Boyle's Law means, I was able to determine that by multiplying pressure and volume together, I should be getting a constant value throughout each trial. So as I increase the pressure, the volume should decrease at a proportional level, giving me a constant K value throughout every single trial. So here is me actually running experiments using the Boyle's Law apparatus. So right now I'm entering some data in the computer, but so as you'll see here, this is me increasing the pressure level over in the reservoir cylinder. So by pumping that up, the pressure is being increased, and you can see the test cylinder, the fluid levels actually rising, decreasing the volume, showing that inversely proportional property that Boyle's Law shows. So now, the important thing of this experiment is keeping our both cylinders at a constant temperature. So I'm currently waiting for the temperature to even out, because when I increase the pressure, the temperature rises slightly. So once that temperature gets back to a good level, which I think was around like 27.9 degrees Celsius, I'm able to look at the height once again and enter the data. So as that volume's decreasing, I can move the height meter to actually be able to measure the volume change that occurred, and then I can enter it into my table. Okay, so here are the results for my experiment. Starting with this first table, this was kind of some of the preliminary information I needed before I actually conducted the experiment. The first is the diameter of the test cylinder in millimeters, followed by the area, as well as the temperature that we wanted to keep a constant value the entire time, and the local pressure, the atmospheric pressure. So we ran a total of 11 trials, starting with an absolute pressure of 1.01325, which is just the atmospheric pressure, and ending at 3.01325, which is a gauge pressure of 2 bar. We increased by increments of 0.2 bar during each trial. And so our first piece of information was the digital indicator reading. That was the height that I was changing, and as you can see, it slowly decreases with each trial. We also have the volume, which we were able to calculate from the height, as well as 1 over the volume, and then our constant K value. So here are two charts that I made. The first one is just a simple pressure and volume chart, and it shows that curved relationship that we are looking for between pressure and volume to get a constant K value. The second is our second chart, which is showing the relationship between absolute pressure and 1 over the volume, which gives us that linear relationship that we are looking for. Big thing to note during this experiment is that our hypothesis stated that when we were multiplying P and V together, we should get a constant K value. As you can see, our first value is that 0.08871, and then we end with a 0.085025, and there is a slow, very slight decrease in that K value as we increase the trial. This is due to some human error on my part, I assume. If I had to guess, it'd be the temperature readings. The room was cooling down slightly as the experiment went on, so that is a likely result for why the pressure and volume don't exactly equal a constant the entire experiment. However, it is a very close reading. So that's the results of my experiment, and thank you very much, and have a good rest of your year.